Good afternoon, sir.
Good afternoon, all of you. Am I audible?
Yes, sir. Yes, sir. You are audible.
Okay. So now I request you, Dr. Laxmi Mishra, to deliver his lecture on solvable groups. Dr. Mishra.
Thank you, sir. Am I clearly audible today?
Yeah.
Since my microphone was not working properly yesterday, so I'm asking.
Very clearly, Laxmi.
Okay, sir. Pranam, sir. Okay, so let me start. Share my screen. Is my screen visible? Okay. So let us start. Okay. Yesterday I defined solvable groups. Okay. So one thing I told wrong. That means that was mistake. That I told that this.
Lakshmikant sir, your screen is not visible.
My screen is not visible. Okay.
Yeah, it is written that you have started screen sharing, but it is not visible, all of us.
Okay. I am restarting it again. Is it visible now?
Yes, it is.
That's fine. Okay. So yesterday I told that this Z6 has a subgroup. This is generated by 3, which is nothing but isomorphic to Z2. So I told that Z6 by this Z3, it was isomorphic to Z3, which was I told that it was isomorphic to Z2, which was incorrect. So it will be isomorphic to Z3. Okay. And similarly, I told that this quotient group was isomorphic to Z3, which was incorrect. So this will be Z2. This was the mistake. So now let us start. So just why are we studying solvable groups? You know very well. And solvability is what? The solvability is just a measure of group, how far this group is from being abelian. Okay. So if it is abelian, you know very well that it has a solvable series. This one, so it is not so far. Okay. It is very close. Okay, and if we see that S4 is solvable, but it has a solvable series like S4, which contains A4 contains V4, and V4 contains identity. Okay, so it is these steps far from being abelian, and okay, so solubility nothing but a measure of how far the group is from being abelian. Okay, okay, so now let us move to some more results and examples. So yesterday I told that if if G is if H is a soluble subgroup, okay, H is a soluble subgroup, and a soluble normal subgroup, and G by H is also soluble, then G is also, okay, I told yesterday. So now just we are going to some more results, like if we have H and K are two subgroups of G, and K is normal subgroup of G, then we know very well that HK is what? In this case, HK is a subgroup of G. In general, HK may not be a subgroup of G. Okay, you know, but it becomes a subgroup if HK is subgroup of G if and only if HK is same as KH. Okay, so in particular, if we take K normal in G, then in that case you can say that HK is same as KH, so HK is normal here. HK is not normal, but HK is subgroup of G here. Okay, so we are going to show that if H and K both are soluble subgroups, okay, soluble subgroups of G, and K is normal in G, okay, then G, not G, but HK is also soluble. Okay, this is a very simple. If we wish to prove, then you know that by second isomorphism theorem, H by H intersection K, which is isomorphic to HK by K. Okay, so we know that H is soluble. Okay, and H is soluble, and this one is soluble. Why this is soluble? Since it is a quotient of factor group of H, factor group of soluble group. Since H is soluble, so its factor group, this is also soluble, and this is soluble, then we can say that this HK by K is also soluble. Okay, so from here we are seeing that K and HK by K both are soluble. K and HK by K both are soluble. Hence, we can say that HK is also soluble. Okay, so this one is the result, that if we are taking H and K, both are soluble subgroups, and K is normal in G, in this case, this HK becomes soluble. But in general, this is not true, even if HK is equal to KH in general. Okay, So you can see its example. So now let us move further. So uh, just I told that yesterday that if we are taking H and K two groups, and if H and K both are solvable, then this H cross K is also solvable. Okay, if both are solvable. Okay, so how will you prove it? Simply, if it is G, then you know very well that this H cross K is such a group in which H is also normal. Okay, H is normal in H cross K, and H is not exactly normal, but H is normal in the form of H cross singleton identity. This is isomorphic to H, and this is normal subgroup of H cross K. Similarly, K is also normal subgroup of not in this form, but we can say this. This is normal in H cross K. Okay, so both are normal. And one more observation you can do, that is if we take quotient group. Okay, so quotient group of this one is nothing but it is isomorphic to K. Okay, so using this one we can say that H is given soluble, and its factor group is also solvable from here. So from here we can say H cross K is also solvable. Okay, is it correct? Are you understanding? I'm waiting for your response. Okay, that's good. That's good. So let us move further. We can generalize it. Uh, how can we generalize it? Do you know what is semi-direct product? Do you know? No? Yes. Okay. Anupam, yes. Okay. So I'm just recalling it. What is a semi-direct product of two groups? Okay. Suppose we have two groups, H and K. These are two groups, and we are defining. Uh, suppose G is what? G is nothing but H cross K. That means it is collection of all ordered pairs of H and K. Okay. So let us define and one more thing. There is what a map homomorphism phi is given. It is already given from group K to odd H. What is odd H? You know, this is a collection of all automorphisms from H to H. Collection of all automorphisms from H to H. Okay. So this phi is homomorphism. Okay, this is given homomorphism. This is given. Okay. So now we are defining a binary operation on G. How will we define? We just define suppose we have two elements H1 K1 and H2 K2. So what is their product? If we are defining direct product, that means in that case, how we define? We define H1 H2 here operation of G1 H and K1 K2. This is operation of K. Okay, so in this case we are not defining in this manner. We will define in another way, like how will we define? This is H1 and we somewhat tilt H2 by means of K1. So phi of K1, you know what is phi of K1? Phi of K1 is some automorphism of H. So it will be operated on H2. It will give some another element of H. Okay, so this is the first coordinate and the second coordinate is same. Okay, so we are defining this one, this star here. So you can check this G means H cross K with is a group with this operation. You can check. This is just an easy exercise. You can check. So if it is a group, then you can say that H is also sitting inside G. In which form? H is sitting in the form of H cross singleton identity. This is sitting inside G. Okay. Similarly, K is also sitting inside G in the form of this one. Okay. Okay. And you can also observe that H is normal here. H is normal here, but K is not. K may not be. Okay. It will depend on this phi. K may not be normal. Okay, so we can't say it is not normal, but it may not be normal. Okay, so one more thing you can say that if we take quotient group G by H, then what we'll get? We will get it is K. Okay, so now what we wish to show? We just wish to show, not to show, but yes, I'm stating it that if H and K are two groups, okay, two groups and soluble groups, okay, H and K, these are two soluble groups, then it will imply, yes, one more thing I forgot to mention, that this G is denoted by H semi-direct product K. Okay, this is notation for semi-direct product. Okay, and okay, so this triangle tells that which one is normal, H is normal or K is normal. Okay, so here H is normal, so you are seeing this triangle is telling. Okay, so H and K are soluble, then their semi-direct product H semi-direct product K is also soluble. Okay, so proof is just same, using similar technique. Okay, what is the technique? Technique is that H is given normal, given soluble, and G by H is K, which is also soluble. So using previous result, we can say that this H semi-direct product K is also soluble. Okay. So this is just a generalization of previous one. That means direct product. Okay. So some more things you can. Okay. There is one thing that is what? Okay. So if we have a finite group, okay. So suppose we have a finite group, which is soluble. I'm just stating this result. I will not prove it. Okay. So if G is finite group and soluble, okay, then it is equivalent to saying that if D is a divisor of order of group such that the GCD of order of D and order of D divided by order of G divided by D, this is 1. That means these two are coprime. Then G has a subgroup of order D. Okay. So in some sense, it is what? This is a Lagrange theorem like thing. Okay. So you know what is Lagrange theorem? Lagrange theorem says that whenever D divides order of group where G is finite, then why this is not sorry, it is somewhat another thing. It is not Lagrange theorem like thing. Okay. So Lagrange theorem already holds in group, so it is not that. Okay. So I'm just telling one more thing, but forget it. What I have told that G is finite group and soluble. Okay. So whenever D is such a factor of order of group uh, which is co-prime with the order of G by D, then G must have a subgroup of order D. Okay. So in this way, we can say that what can we say? It's a particular corollary like thing. It's a corollary of this one that if we are taking some CLT group, okay? So every CLT group is soluble. Okay. So this is somewhat I think it is just a corollary of this one. Okay. So what is CLT group? I think you will know what is CLT group. CLT group is just those groups in which full converse of Lagrange theorem holds. And you know what is the Lagrange theorem? Lagrange theorem says that if D is some divisor of order of group where G is finite, okay, then D is then there is a subgroup H of G of order D. Okay, so this is Lagrange theorem, but you know very well that Converse of Lagrange theorem generally doesn't hold. That means, for example, if we take alternating group of degree 4, okay, so in A4, you know that there is no subgroup. 6 divides order of A4, which is nothing but 12, but there is no no subgroup of A4 of order 6. Okay, so this is Lagrange theorem, and its a full converse doesn't hold. Okay, similarly, yes, Rahul. Okay, so those groups in which a group in which full converse of Lagrange's theorem, not Lagrange's theorem, holds. Okay, so what are some examples? Every abelian group is CLT. Okay, that means in abelian groups, converse of Lagrange theorem holds. Okay, and one more thing. Okay, so S4 is also CLT. For every divisor of order of S4, there is a subgroup of S4. Okay, so this is CLT, and CLT groups are solvable. Why CLT groups are solvable? Since if D is such a D is any divisor which satisfies this condition. Okay, so there is a subgroup of order D. Since it is a CLT group, so it is satisfying this condition. Therefore, it is solved by this proposition. Okay, so I think you will be understanding this one. Next one is now let us move some more results. So proposition is that a group G of order PQ, where P and Q are primes, okay, is also solvable. Okay, you can also see its proof. It is also very obvious. Okay, so this one is another result, and I will tell some more results, but before that I am one more thing which is very much important. That is what if we have some finite group. Okay. Suppose G is a finite group. Okay, so it's okay. It is equivalent to saying that it has a composition series with factor group factor group of prime order. Okay, you know what is the composition series? Composition series is okay, so it is a normal series, okay, and in which every factor groups are simple. Okay, so I think I am correct. Yes, Rahul. So this is if G is a finite group, then it has a composition series with this with a factor group which is of prime order. Okay, so that means what we can say G equals 0 and G1 and so on. There is Gn, which is identity with the Gi by Gi plus 1 is cyclic group. Obviously, every group of prime order is cyclic. So cyclic group of prime order. Okay. So this is another result, and I'm not going to its proof. Okay. So one more thing was already told by I think Vivek Jansser that every nilpotent group is solvable. Okay. I don't know whether he told or not, but he will be. If he had not told, then he will be telling nilpotent groups are solvable. Okay. Yes, it is. Obviously, it is very trivial. And another result is suppose you know. I think you will be knowing what is super soluble groups. Super soluble groups. What are super soluble groups? Just it is a group with a normal series. It has a normal series. Okay. In which every Gi is normal in G, and the factor group is what? Yes, Gi by Gi plus 1 each is I think it is cyclic. Okay. I hope I am not wrong. Okay. Super soluble groups are those groups. Super soluble groups are those groups which have a normal series like this, and every subnormal subgroups are normal in G, and factor groups are cyclic. Okay. So result is what? We can give some examples of it. So every abelian group is, first thing is every abelian group is super soluble. Okay. Okay, every abelian group is super soluble. So, but and one more thing is that what is that every super soluble group is soluble. Every super soluble group is soluble. It is by definition. I think you will understanding, since gi by gi plus 1 is cyclic, so it is abelian. Hence this is this G is solvable group. Okay, but converse may not be true. Okay, converse of above may not be true. Okay, so what is converse? Converse is that if G is a solvable group, then it may not be super solvable. So what is example? Do you have some example? I hope you will be having some example. Okay, so just yes, yes, 4. S4 is solvable. We know this is solvable, but it is not super solvable. But not super solvable. Why it is not super solvable? Since S4 has a normal series, a solvable series, S4 by A4 and A4 by okay, I may be wrong. Just one thing. I think it is super solvable. So just a minute, okay? Just a minute. Yeah, we can take another example, I think. Yes, but we have some this one, okay? And in this case, it is what? Every factor group is cyclic in this case, okay? So this is not super solvable. So this is super solvable, okay? And I'm wrong. This is super solvable. Solvable as well as it is super solvable also. But what? Just 1 minute. Okay, just take another example like A4 cross Z, Z3. If we are taking, yes, Anupam, you're saying it is a quaternion group of order 8, but I don't think so. Quaternion group of order 8 is also super solvable, okay? Since it has yeah, it has okay. This is generated by I, that means it is of order 4, and it has a normal subgroup -1, 1, and which has a normal subgroup singleton. Okay, so this one is okay. So therefore this is super solvable. Okay, this one I'm taking this one. Okay, so this is solvable. I hope this is solvable. Okay. This is solvable. It is so. Yes, it is being direct product of two solvable groups, so it is solvable, but it is not super solvable. I have to check. This is not super solvable, but it is 100% that it is not super solvable. Okay, so this is solvable but not super solvable. This one is an example. Okay, so let us move further. Okay, so you have already I think studied what is group extension. Group extension. Okay. Yes, group extension. Well, what is group extension? Suppose we have two groups, H and K. Okay, so these are two groups, and am I audible? Since my internet connection is something disturbing, so I'm audible. Yes, yes. Okay, Rahul. So H and K are two groups. So what is a group G? A group G is extension of K by H. Okay, if H is that means I'm just defining this one. So singleton identity to H to G to K. There is some function, some homomorphism F, and G is another homomorphism, such that this is F is what? F is 1 1, and G is onto, and kernel of G is image of F. Okay. Yes, Anupam. Actually, it is just definition. So this is extension of K by H. I was also thinking about it, but there is it is given by definition. It is the extension of K by H. Okay, so okay, it is definition, standard definition, I think. So this G is called, this G is called extension of K by H. Okay, if this condition holds. So okay, so now what is result? Result is that if H and K both are solvable, then extension of K by H is also solvable. Okay. Gunjan, you are saying that GLN5 is super solvable or not? Okay, you are asking. Okay, I think I have to check. Okay, so I can't say anything right now, so I have to check it. Okay, so what is our result? This is saying that H and K both are soluble, then its extension is also extension of K by H is also soluble. This is another result. But now we have to tell what is a radical of a group. Okay, so I'm telling here. Just one thing, observe that if now what is maximal subgroup? You know, I think maximal subgroup of group G. Okay, so suppose G is a group and H is a subgroup of G, which is not equal to G. Then this H is maximal in G if there is no proper subgroup of G containing H except H itself. Okay, that means if there is another subgroup in between H and G, then it must be equal to H. Okay, so if there is another subgroup H1 of G, which is not equal to, which is this is proper, okay, and it is containing H, then it must be equal to H1. Okay, so this H is what? H is maximal subgroup, and you know very well that maximal subgroups may or may not exist in a group. Okay, so for example, in cyclic group of order, cyclic group of infinite order. Okay, so that is Z. What are maximal subgroups? You know, I hope you will know that any subgroup of Z is of the form MZ for some M. Okay, I think you will be knowing this one. So this is any subgroup. So when will it be maximal subgroup? And you know, if there are two subgroups like MZ and NZ. So MZ is contained in NZ is only what? N divides M. Okay, that's good. That's good, Rahul. I'm going to that. So MZ is if MZ is contained in MZ, then N divides M. That means if we can say 4Z is contained in 2Z. Okay, since 2 divides 4, so 4Z is contained in 2Z. Okay, so now if I'm saying that MZ is maximal, then MZ is not contained in any subgroup of Z except Z. Okay, that means no other proper subgroup of Z is containing MZ except MZ. Okay, so that means M has no proper divisor. Okay, So M has no proper divisor. That means M is what? M is prime. So then M is prime. That is PZ, where P is prime, is maximal subgroup of Z. Okay, here P is prime. So this is maximal subgroup, and I told that maximal subgroup may or may not exist. So, for example, if I'm taking QZ, Q, okay, so there is no maximal subgroup in Q. Okay, you can check. So there is no maximal subgroup. There is no maximal subgroup. Okay, now let us come to our topic, that if we are taking some maximal solvable normal subgroup of G, so maximal solvable normal subgroup of group G, so it may or may not exist. Okay, for general G, it may or may not exist. So if it exists, then is what? This is the largest one, largest solvable normal subgroup. Okay, so you know what largest means. That means there is no other subgroup, proper subgroup of G which contains that group, that subgroup. Okay, so what is the difference between maximal subgroup and largest subgroup? You know, I think maximal subgroups may not be unique, but largest subgroup is unique. Okay, so okay, you will be knowing that if we take a cyclic group of any cyclic group. Okay, so there is, so suppose I'm taking simple example like Z something Z12. Okay, so there is a which one? There is a subgroup which is generated by 2 bar. Okay, and that is maximal. Yes. Okay, and that is also largest. Okay, so in Z12, the subgroup of order 6. Okay, so subgroup of order 6 is maximal, and it is also largest. So some in another examples, you can say maximal. There, yeah, in this example, you are seeing there are so many maximal subgroups. Okay, but I don't know which one is largest. Okay, so yes, how will you show it? This result, if any maximal solvable normal subgroup of G is largest. So if you have some maximal normal solvable normal subgroup H of G, and suppose K is another solvable normal subgroup, and this H is maximal. Okay, maximal solvable normal subgroup. So HK is what? HK is also soluble. which is also soluble subgroup of G. Okay, but since H is maximal, so it will be nothing but Hk is equal to H. In this case, you can say that K is contained in H. Okay, so this H is largest. That means H is what? This is largest. So any other soluble normal subgroup is contained in this one, this H. So this is largest. So what is now? I'm defining this one, that radical is, what is radical of a group? So a radical, wait a minute, radical of a group. So let G be a group. Okay, and radical of this group is what? Then radical of G is maximal, not maximal, but largest, is the largest solvable normal subgroup, and you know it may or may not exist. So if it exists, okay. So radical of a group is what? This is nothing but the largest solvable normal subgroup, okay, of G. So for example, what is example? Suppose G is abelian. If G is abelian, then what can you say? You have to take maximal largest solvable normal subgroup. Oh, sorry, I'm just taking a wrong example. But if we take S4, okay, symmetric group of degree 4, then you know what is maximal solvable normal subgroup. Okay, it has normal subgroups are what? So A4, not V4. V4 is not normal, and singleton identity. Okay, so these two are normal subgroups, and this one is largest. Okay, so radical of S4 is nothing but A4. Okay, so this is radical, and what is a semi-simple group? It is semi-simple group. It is a group with trivial radical. Semi-simple group is what? It is a group with trivial radical is called semi-simple group, and this semi-simple group is very much important in higher algebra. Okay, so you will see. I think I have much more things to say, but I should stop, and some whatever left in soluble groups, that will be discussed by Vivek, Jansser, and Swapnil sir also. Okay, so I think Seema Moria is asking about its example. So, what is example? Just take Z5. Okay. So Z5 is what? Z5 has it is already solvable. Okay, and it is normal in itself, so its radical will be I think its radical will be Z5. Wait a minute.
मेरा वीडियो क्यों नहीं दिख रहा? मेरा वीडियो दिख रहा है? Am I audible, sir? Okay.
Yes, you are audible, but I was thinking about something, and Seema, it will be told. I will tell.
Thank you, sir.
Okay.
I, Ramji Pandey, on behalf of Professor P.L. Sharma, Higher Education Trust and Department of Mathematics, EWING Christian College, Prayagraj, express our sincere thanks to Dr. Laxmi Mishra from Bhavan's Mehta Mahavidyalaya, Bharwari, for sparing his valuable time from his busy schedule for invited lectures. Once again, thank you, sir. Now,
Thank you,
there is
Ram.
an announcement for all the participants. A feedback form for all the participants about this workshop is available and will be shared in the chat box after the second session. All the participants will require to submit the feedback after the end of next session, that is 5:15 p.m. Now we will wait for 5 minutes and will resume in 5 minutes for the second session with our keynote speaker, Dr. Vivek Kumar Jansser.
Vivek sir, are you present?
Yes, I am here.
Okay. Thank you. So now I invite Dr. Vivek Kumar Jain for his lecture. Sir.
Thank you, sir. So let me share the screen and then we will start. Good afternoon, everybody. Are you able to see my shared screen?
Yes.
My voice is clear.
But your video is not coming.
Okay. Yes. Is it there? Yes, it is.
Yeah, it is okay. No.
Okay. So let me recall what we have done quickly and then we will proceed. Okay, so what we have done yesterday is that we have defined lower central series and L0G, L1G, L2G and so on. So L0G is G, L1G is GG, that is the commutator subgroup, and L2G is commutator of G and L1G and so on. So this was the lower central series. Similarly, we have defined the upper central series, Z0G, Z1G, Z2G and Z3G and so on, where Zn plus 1G, a quotient with Zng, was equal to the center of G by Zng. So in this way, and the definition of nilpotent group was Lng is trivial or Zng is trivial for some n, then the group G is called nilpotent group. Okay. And there was another definition. A group G is called nilpotent of class n if Lng is equal to identity or trivial group, but Ln minus 1G is not equal to trivial. Okay, now see this definition. Here we have actually taken n belongs to n. Okay, so with this definition, we have nilpotent group of class 1, nilpotent group of class 2 and so on. But if you see the group to be trivial group or the group of order 1, then for that group L0G is trivial. But you cannot have L0 minus 1. You cannot talk about this. So this group does not fit in this definition. But by convention, we are taking that the nilpotency class of this group is 0. Okay, so let me write it. Trivial group is regarded as nilpotent group of class 0. Trivial group means group of order 1 is regarded as nilpotent group of class 1. Group of class. Okay, sorry, group of class 0. So trivial group को हम लोग group of class 0 मान के चलेंगे और बाकी हम लोग ने, so we have seen in the last lecture that what is the group of class 1. And one more thing which we have proved in the last lecture is if G is a nilpotent group of class n, then ln minus 1g will always be contained in the center of G. So center of G is non-trivial. And nilpotent group of class 1 means abelian group, except trivial group. Trivial group is regarded as nilpotent group of class 0. And then we have seen that Q8 is a nilpotent group of class 2, D4 is a nilpotent group of class 2, D5 is not a nilpotent group. And we have also seen that every nilpotent group is solvable. Then we have proved that subgroup of a nilpotent group is nilpotent. Homomorphic image of a nilpotent group is nilpotent. We have also done it. So I think there is no problem till now. If you have any problem up to now, then you may ask, or we may proceed. Okay, so let us proceed now. So now we will talk about direct product of two nilpotent groups. So the proposition is direct product of two nilpotent group is nilpotent. Let us prove it. Suppose H and K are two nilpotent groups of class, suppose A and B respectively. Suppose I have taken two nilpotent group. The class of one is A and the class of another is B. Now we are to show that H cross K, that is the direct product of H and K, is nilpotent. To prove it, I have a claim that ln of H cross K is equal to ln of H cross ln of K. If we prove this claim, then the things will be proved. Why? Because if n is greater than A, then ln of H will become trivial group. And if n will be greater than B, then ln of K will be trivial group. So if n will be greater than equal to the maximum of A and B, then this ln H and ln K both will be trivial, so their product will be a trivial group. So ln H cross K will become a trivial group. So it simply means that this H cross K will be a nilpotent group. So to prove this proposition, it is sufficient to prove this claim. So let us prove this claim by induction. So proof of claim. Proof of claim. This proof will be by induction on n. And n is a number from this set. Okay. Now, so for n is equal to 0, L naught H cross K, by definition of L naught, it is H cross K, and by definition of L naught again, it can be written as L naught of H cross L naught of K. So for n is equal to 0, this holds. So by induction, suppose Lm of H cross K is equal to Lm of H cross Lm of K for some m in n. So what we have to show now? We have to show that Lm plus 1 H cross K is equal to Lm plus 1 H cross Lm plus 1 K. Okay, so let us calculate Lm plus 1 H cross K. So by definition, what is this term? This is H cross K, comma, Lm H cross K. I hope you agree at this point. Now, by induction hypothesis, Lm of H cross K is Lm of H cross Lm of K. This is by induction. So we have assumed for m, and we have to show it for m plus 1. Okay. Now what is this set? This is a commutator, and commutator is generated by this type of element. So H comma K, H comma K, comma H dash K dash, bracket, such that H belongs to H, H dash belongs to LMH, K belongs to K, and K dash belongs to LMK. Okay, so we have just applied the definition, nothing more than that. Now this is commutator, and by definition of commutator, we can write it as HK inverse, H dash K dash inverse, HK, and H dash K dash, such that rest is same. And now apply the definition. Because it is a direct product, inverse can be taken on each of the components, and then the product is also component wise multiplication. So we can write it as bracket H dash commutator, and in second place K dash commutator, such that H belongs to H, K belongs to K, H dash belongs to LMH, and K dash belongs to LMK. Okay, I hope there is no problem till now. Now what is this? This H belongs to capital H, and H dash belongs to LMH, and this is the direct product. So you may, and each of the elements of this, each of the generator of this group is of this form. So it simply means that you may write it as H commutator LMH, the first component is coming from it, and cross K LMK. So this is nothing but Lm plus 1 H cross Lm plus 1 K. And this is what we want to prove. And this proves the claim. Hence, Lm of H cross K is equal to LMH cross LMK for all M in N union 0. So take alpha to be maximum of A and B, where A is the nilpotency class of H and B is the nilpotence class of K. So what is L alpha H cross K? This is L alpha H cross L alpha of K. So this is trivial and this is again trivial. So this is a trivial H cross K. So H cross K is nilpotent of class alpha is equal to maximum of AB. Is it okay? So direct product of two nilpotent group is nilpotent. So because we have proved it for two, so we can say that direct product of finitely many nilpotent group, direct product of finitely many nilpotent groups is nilpotent. Note one thing, that we have talked about direct product, but semi-direct product of nilpotent group need not be nilpotent. For example, if you take S3 symmetric group on 3 symbols, then you may take a subgroup of it H to be identity permutation 1, 2, 3 and 1, 3, 2. So as you know, this is a normal subgroup of it, and take another subgroup K to be identity and 1, 2. Then H is normal, K is not normal, but HK is equal to S3. So it is a semi-direct product of H and K. So S3 is semi-direct product of H and K. H is abelian, so it is nilpotent. K is abelian, so it is also nilpotent. But their semi-direct product HK is not nilpotent group. So semi-direct product of nilpotent group did not be nilpotent. Okay. Now we are going to prove another proposition. Suppose that G by ZG is nilpotent of class M. Then G is nilpotent class M plus 1. So suppose we have a group G and we quotient it by center, and this G by ZG is nilpotent. Then the group G will also be nilpotent. So let us prove this thing. Okay, so how will we prove it? We have to show that G is nilpotent of class M plus M. Okay, so if you see, let us do some rough work and then we will come to actual proof. If you see the upper central series of G, why we are using the upper central series of G? Because in upper central series, this term ZG is involved everywhere. Center of the group is involved everywhere. So that's why I am going to use upper central series for this proof. So if you consider the upper central series of the group G, then how this series look like? This is Z0 G and then Z1 G, Z2 G. So of course this is trivial, Z0 G is trivial, Z1 G is center of G, and so on. And what we have to show is that Z M plus 1 G is equal to G. This is what we want to show. Do you agree at this point? Now, what is the definition of this Z2G? Definition of this Z2G is Z2G upon Z1G, that is the center of G, is equal to the center of G upon Z1G. Center of G upon Z1G. And what is the center of G upon Z1G? If you consider the upper central series for G by ZG, the upper central series of G by ZG is, first term is Z0 G by ZG. Then we have Z1 G by ZG. Then we have Z2 G by ZG. And so on. And it is given that Zm G by ZG is equal to G by ZG. This is given. I have not started the proof. I am just telling you what are the things which is given. Okay, and now what is Z1 G by ZG? Z1 G by ZG is the center of G by ZG. So as you can see here, center of G by Z1G, Z1G is equal to ZG, is nothing but Z1 of G by ZG. Okay, so you may see here Z2G upon Z1G is same as Z1 of G by ZG. Okay, it is clear from definition. And what we have to show is that Zm plus 1G is equal to G. Okay, so from here we can guess one formula. If it is true or not, whether it is true or not, we will verify. But as you can see, Z2G by Z1G. So if I write it as Zi plus 1G upon Zig, then it seems that it may equal to Zi of G by Z. Okay, from here we can guess this formula. And now we will prove first this thing, that this is true by induction on I, and then we will be able to prove very easily that if Zm G by Zg is G by Zg, then Zm plus 1G is equal to G. Okay, so let us start the proof. So this was the rough work, just to understand the things. Let us start the proof. Suppose G by Zg is a nilpotent group of class M. Suppose it is a nilpotent group of class M. Okay, now my claim is that, claim is this formula, that Zid I G by Zg is same as Zi plus 1G upon Zg. Let me prove this claim. Proof of claim. So this proof is by induction on I. For I is equal to 1, Z1G by Zg. As we have seen above, by definition, it is Z2G by Zg. Okay, so you may again see it. This is Z2G by Z1G. Sorry, so Z1G is Z. So this is Z2G by Z. Okay, so for I is equal to 1, it is true. Suppose claim is true for I is equal to M. Okay, so suppose this claim is true for I is equal to M. Now, so what we have to do? We have to prove it for I is equal to M plus 1. So I is equal to 1 means what? Let me write it here. That is Z M G by Zg is equal to Z M plus 1 G by Zg. Okay. Now by definition, what is Z M plus 1 G by Zg upon Zm G by Zg? This is same thing as the center of G by Zg upon Zm of G by ZG. Do you agree? This is the definition of upper central series which we are using here. And now by induction, this Zm G by Zg can be written as Zm plus 1 G by Zg. So we can write it as the center of G by Zg upon Zm plus 1 G by Zg. I hope you agree at this point. There's no problem. Now, you know the isomorphism theorem. Isomorphism theorem says that if you have a group G, you quotient it with some normal subgroup K, H is another normal subgroup which contains K, then this is isomorphic to G by H. This is the isomorphism theorem. So let us use it here. So we can write it as G by Z m plus 1 G. Okay. But you know what is ZG upon Zm plus 1? By definition, it is nothing but Zm plus 2 G upon Zm plus 1 G, by definition of upper central series. Now again, this term is actually isomorphic to Zm plus 2 G by Zg upon Zm plus 1 G by Zg. Okay, these terms are isomorphic, but for our convenience, I am just writing equal here. These all are isomorphic. Okay, by this isomorphism, because center is always contained in the higher term of upper central series. So we can write it like this. And now, what is this? Yes, what is this? This thing, so let me write it here from where we have started. Zm plus 1 G by Zg upon Zm G by Zg Okay. Now see, what is Zm plus 1 G by Zg? Zm plus 1 G by Zg is by induction can be written as Zm of G by Zg. Okay, so we can write it as in the denominator Zm of G by Zg, and in the numerator it is Zm plus 2G upon Zg. Okay, so this implies Zm plus 1 G by Zg, G by Zg. Let me write it clearly. G by Zc is equal to Zm plus 2G by Zc. And see, this is what we want to prove by induction. Or you may say that this is our claim to prove. So this proves our claim. Just see the claim. This is our claim. For I is equal to 1, we have shown. For I is equal to m, we have assumed. And for I is equal to m plus 1 is proved. So this proves the claim. Proved. Okay. So once this is proved, so now Zm of G by Zg is equal to G by Zg. Why? Because G by Zg is a nilpotent group of class M. This was our assumption. So Zm G by Zg can be written as, by this formula, which we have proved just now. This can be written as Z M plus 1 G by Zg, and this is equal to G by Zg. So it simply means that Zm plus 1, this simply means that Zm plus 1G is equal to G. This implies G is nilpotent group of class M plus 1. And this proves the proposition. So if G by Zg is a nilpotent group of class M, then G is a nilpotent group of class M plus 1. Okay. Now, there is a small corollary for this proposition. Suppose H is a subgroup of center of a group G, and G by H is nilpotent. Then G is nilpotent. So we can prove this corollary with the help of above proposition. Now, what is G by H upon Zg by H? By isomorphism theorem, it is isomorphic to G by Zg. So you may say that G by Zg is quotient of G by H, or G by Zg is homomorphic image of G by H. So this implies, so let me write here, suppose G by H is nilpotent, and since the quotient of or homomorphic image of nilpotent group is nilpotent, so this implies G by Zg is nilpotent. This is nilpotent, and by above theorem, above proposition, G is nilpotent. So what does it mean? It means that if central quotient means quotient by a central subgroup, that is a subgroup contained in the center. If the central quotient is nilpotent, then the group is nilpotent. One remark. In case of soluble group, you have seen one result, and the result was, if H is a normal subgroup of G, I am writing it in short. In case of soluble group, H is soluble, G by H is soluble, implies G is soluble. But it is not true in case of nilpotent group. For example, take G to be S3, take H to be the subgroup, 1, 2, 3, 1, 3, 2. Of course, this is a normal subgroup of S3. This is also soluble. H is soluble. G by H, the order of G by H is 2. So it is an abelian group. So G by H is soluble. But you know G is not soluble. So this thing is not true in case of, sorry, sir. Let me, H is nilpotent. G by H is nilpotent because its order is 2 and it is abelian, nilpotent. And G is not nilpotent. Okay. So the result which is true for soluble group, this result is not true for nilpotent group. There is another result which is true for nilpotent group, and that is a proposition or you may say this is a theorem by P. Hall. P. Hall was a mathematician on, this is called the P. Hall criteria for nilpotence. If n is normal in G and n G by n dash means commutator of n are nilpotent, then if these two are nilpotent, then G is nilpotent. So this is the result. We are not going to prove this result, but in case of soluble group, it was G by n is soluble, n is soluble, and G by n is soluble, then G is soluble. But in case of nilpotent group, it is n is nilpotent and G by n dash is nilpotent, then G is nilpotent. This is called P. Hall criteria for nilpotence. Okay. Now come to another proposition. The proposition is, if we take a finite P group, then finite P group is nilpotent. Every finite P group is nilpotent. Proof. Now note one thing, if you have a finite P group, then the order of finite P group is P to the power n for some n in natural number set. Okay, so what I am saying is that if we have G is finite P group, if and only if order of G is P to the power n for some n in n. Okay. So actually what is P group? P group means if we take any element, a group is called P group. If we take any element of the group, then the order of that element is a power of P. Then that group is called P group. So if you have a finite P group, then the order of the group will be P to the power n. Okay. Because if it is not P to the power n and some another prime Q is involved in it, then by Silo theorem, in that finite group, there will be an element of order Q. And that is not possible because the group is P group. So if you have a finite P group, then its order will be P to the power n for some n. And if you have a group of order P to the power n, then each of its elements will have order a power of P, so that will be P group. So every finite P group has order P to the power n for some n. Okay, so we have to prove that every finite P group is nilpotent. There is one more result for a P group. So let me state that result and then we'll proceed. If order of G is P to the power n, where P is a prime, then center of G, or you may say P divides the order of center of G. So center of G is non-trivial. This is another result which you can obtain with the help of group action or by class equation, you may say. So I'm not going to prove this result, but you may see it in the book which we have referred. So I will use this fact to prove that every finite P group is nilpotent. Okay. Suppose, so we will prove it by induction. On n. So a finite P group has order P to the power n for some n, and for this n we will use induction. For n is equal to 1, so finite P group, let me call it G, has order P to the power n. So for n is equal to 1, order of G is P, so G is cyclic group, and cyclic group is abelian, so G is nilpotent. I hope this is okay for you. So a group of order P is always nilpotent. Now, by induction hypothesis, assume that any group of order P to the power m, where m is less than n, is nilpotent. We will show group of order P to the power n is nilpotent. So once we show that the group of order P to the power n is nilpotent, then any group of order P to the power n is nilpotent for all n. Okay, so let us show it. So by induction, we are going to prove. So suppose G is a group of order P to the power n. Now, P divides the center of G by this result. Then, if we quotient G by center of G, then what will be the order of this group? This order of this group will be P to the power K, where K is strictly less than n. So by induction, G by ZG is nilpotent. Why? Because we have assumed that any group of order P to the power m, where m is less than n, is nilpotent. So G by ZG is nilpotent. But we have proved that if G by ZG is nilpotent, then G is nilpotent. This implies G is nilpotent. So by induction, any group of order p to the power n is nilpotent for all n in N. Okay, I hope there is no problem in understanding this proof. We have used induction to prove it. For n is equal to 1, first we show the order of group is p, so it is nilpotent. Then we assume that any group of order p to the power m where m is less than n is nilpotent, and then we have shown that a group of order p to the power n is nilpotent. So any group of order p to the power n for any n in the set of natural number is nilpotent. So we may say that p group is nilpotent. Finite p group is nilpotent. Okay. Now there is another proposition, that is let H and K be normal subgroups of a group G such that G by H and G by K are nilpotent then G by H intersection K is nilpotent. Suppose I take two normal subgroup H and K of a group G such that G by H is nilpotent and G by K is nilpotent. Then proposition says that G by H intersection K is also nilpotent. And the proof is simple. Define a map alpha from G to G by H cross G by K as alpha of G is equal to GH and GK. So I am leaving it as exercise for you to verify that alpha is group homomorphism. And what is its kernel? Kernel of alpha is H intersection K. So, by fundamental theorem of group homomorphism, G upon kernel of alpha, that is H intersection K, is isomorphic to alpha of G, homomorphic image of G, which is actually a subgroup of G by H cross G by K. But as you know, G by H is nilpotent, G by K is nilpotent. So this product is nilpotent. This is nilpotent. And we have shown that the subgroup of a nilpotent group is nilpotent. So this is nilpotent. This is nilpotent. And because both are isomorphic, so G by H intersection K is nilpotent. So this group is nilpotent. Okay. Now there is another theorem that is called fitting theorem. Fitting theorem. Let H and K be a normal subgroup of G G is a group and H and K both are normal subgroup of G. And both are nilpotent also. So H and K be normal subgroups of G of class alpha and beta respectively. Class alpha beta mean nilpotency class, so they are nilpotent normal subgroup of G. Then this theorem says that HK is nilpotent of class at most alpha plus beta. You know, if we have a subgroup H and a subgroup K and both are normal, then HK will also be a normal subgroup of G. So what this theorem is saying that if H is a normal subgroup and K is a normal subgroup and both are nilpotent, then their product will also be a nilpotent. And in fact, it is a nilpotent normal subgroup. So this is fitting theorem. I am not going to prove this theorem. You may see its proof from the book of Ramjilal. Okay, but see what this theorem implies. What is the implication of this theorem? Suppose we have several normal nilpotent subgroups in a group G. Then we can take their product and that will give you another normal nilpotent subgroup. So we can talk about a largest normal nilpotent subgroup of the group. Okay, and that will be the subgroup generated by all the normal nilpotent subgroup of G, or you may say then that subgroup will be actually the product of all normal nilpotent subgroup of G, and that subgroup is called fitting subgroup. So let me write here fitting subgroup. Fitting subgroup. So fitting subgroup of a group G is its largest nilpotent normal subgroup. Or you may say it is the fitting subgroup is a subgroup. Fitting subgroup is the subgroup generated by all the normal nilpotent subgroup of G. Okay, so let us see it by example. Suppose G is nilpotent. Nilpotent. Then what will happen? What will be its fitting subgroup? By definition, let us denote this fitting subgroup by FITG. Let us denote fitting subgroup phi fit g. Okay, so if we have a nilpotent group, the group is itself nilpotent, then its largest normal nilpotent subgroup will be G itself. So then the fitting subgroup of G will be G. Okay. So in this way, if you see, then what is the fitting subgroup of Q8? This is Q8. Fitting subgroup of D4. This is D4. What is fitting subgroup of S3? Is it S3? Can anybody answer? What is the largest normal nilpotent subgroup of S3? How many normal subgroups are there in S3? S3 is symmetric group on 3 symbols. As you know, the normal subgroups are trivial group, A3 and S3 itself. And out of these three, 2 are nilpotent, trivial and A3. And the subgroup generated by all the nilpotent normal subgroup, what will be that? That will be A3 itself. Okay, what is fitting subgroup of D5? D5 we have seen it is not nilpotent. And as you can see, it has 2 generator X and Y, and the order of X is 5 and the order of Y is 2. So this subgroup generated by X will be its largest normal nilpotent subgroup. Okay, so the fitting subgroup of D5 is actually the subgroup generated by X, and this is actually isomorphic to Z5, cyclic group of 45. Similarly, fitting subgroup of A4. A4 we have seen it is not nilpotent group. And if you talk about the normal subgroup of A4, then it is V4 and identity. So subgroup V4 is nilpotent also, identity is also nilpotent. So the largest is V4. What is fitting subgroup of S4? Largest normal nilpotent subgroup. Okay, please try to select all normal subgroup which are nilpotent. A4 is normal in S4, but A4 is not nilpotent. V4 is normal in S4, V4 is nilpotent, and trivial subgroup is normal. S4, because it is not nilpotent, so S4 will not come in this list. So normal, largest normal nilpotent subgroup is V4 itself. Okay, so in this way you can determine the fitting subgroup of a group. So thanks to everybody, and if you have any query, then please ask. If there is anything you want to ask, then you may ask. You may write in the chat box. I will try to answer. Okay, if there is no question, then we can end this talk. Okay, over to organizer.
Thank you, Dr. Vivek, for such a nice lecture and the way you have explained difficult thing in such a simple one. Thank you. Now, I invite Professor Ramji Pandey. You want to say something about your feedback
Yes,
form
sir.
or?
Am I audible, sir?
Yes, you are.
Yes.
Sir, there is an announcement for all the participants. The feedback link. 1 second, sir. Okay. There is an announcement for all the participants. The feedback link is shared in the chat box, and all the participants are required to respond the same to ensure the active participation in this workshop. It is also requested to the participants to respond the same before 5:30 p.m. Till then, the meeting will be continued. Okay.